Good evening everyone. So welcome to my YouTube channel Maths Sabdram. So today we are going to see second lecture on infinite series. So let us start today's session now. So today we will study comparison test. Okay. Comparison test. Let summation n goes to 1 to infinity an summation n goes to 1 to infinity bn and summation n goes to 1 to infinity cn be 3 series with non-negative terms. Non-negative terms means it means an is greater than equal to 0, bn is greater than equal to 0, and cn is greater than equal to 0 for or n belongs to n. Okay, such that an is less than cn and cn is less than bn for all n belongs to n. Okay, if then one, if this series n goes to 1 to infinity, bn is convergent, then this series n goes to 1 to infinity, cn is also convergent. Okay. Second, if this series summation n goes to 1 to infinity, an is divergent, then the series n goes to 1 to infinity, cn is also divergent. Okay. So no need to write them here. Okay. So this is one part and this is another part. So let's see its proof, how it will work. Okay. First, let this series n goes to 1 to infinity, 1 to infinity, bn is convergent. Okay. Then this series then S M B is equal to summation n goes to 1 to m, bn is bounded above. Okay. implies there exists k greater than 0 such that SMB is less than equal to k for all m belongs to n. It means partial sum of this series is bounded above. Okay, this is a partial sum. Okay, now put SMC is equal to summation n goes to 1 to m Cn. Then as Cn is less than Bn for all n belongs to n, this implies SMC will be less than SMD, but this is less than k. Okay, so this implies SMC less than. Since this is a monotonically increasing sequence, which is bounded above. Okay, this is bounded above by monotone convergence theorem. Monotone convergence theorem. SMC converges is convergent. Okay, so this implies this series is convergent. Okay, so one is true. Now second one, let this series summation n goes to 1 to infinity an is divergent. Okay, so divergent. Since this series then the sequence Sm a is equal to summation n goes to 1 to m an diverges to plus infinity. Okay, diverges to plus infinity as an is non-negative for all n belongs to n, and this is divergent. Okay, divergent. Since now an is less than bn for all n belongs to n, implies S M A is less than SM B C CN. Now SM diverges to plus infinity and SM A is less than SM C. This implies SM also diverges to plus infinity. So this implies summation n goes to 1 to infinity CN series diverges to plus infinity. It means this series is divergent. Okay. So this theorem is done. Okay. Now theorem, let P belongs to R, then the series summation n goes to 1 to infinity 1 n to the power P is equal to 1 plus 2 to the power P plus 1 upon 3 to the power P and so on is called auxiliary series. Okay. The following holds. What holds? The following holds. Number 1, if P less than the auxiliary series summation n goes to 1 to infinity 1 upon n to the power P diverges to plus infinity. It means the series n goes to 1 to infinity is divergent. Okay. Second, if P is greater than 1, then the auxiliary series summation n goes to 1 to infinity 1 upon n to the power P is convergent. Okay. Okay. Is convergent. Now, note by theorem taking P is equal to 1, we get the series n goes to 1 to infinity 1 upon n diverges to plus infinity. It means this series 1 upon n is divergent. Okay. So we will use this fact very frequently. Now question 1. question 1, or you can say example 1. Example 1. Check the convergence of this series. Okay. Summation n goes to 1 to infinity 1 upon factorial n. So proof solution. Okay. Now 1 upon factorial n is less than 1 upon 2 to the power n minus 1, for all n belongs to n. Okay. Okay. Now let's say, this, you say this an, and you say this bn, and you say this cn. Now, what is this series? Summation n goes to 1 to infinity bn is equal to summation n goes to 1 to infinity 1 upon 2 to the power n. This is a geometric series, and its summation is nothing but 1 minus 1 upon 2, that is 2. It means this series is convergent. This series convergent. This series is convergent. Okay. And this series summation n goes to 1 to cn, that is 1 upon n to 1 to factorial 1 upon n. And this series summation n goes to 1 to infinity bn, that is summation 1 upon 2 to the power n minus r series with non-negative terms, because factorial is also non-negative and 1 upon 2 to the power n is non-negative. Okay. So that cn is less than bn for all n belongs to n. Since this series summation n goes to 1 to the bn, that is summation n goes to 1 to 1 upon 2 to the power n minus 1, is convergent by comparison test by first part, the series summation n goes to summation n goes to 1 to infinity bn is cn is convergent. It means this series 1 to 1 factorial n is convergent. Okay. Now, example 2. Test the convergence of the following series. Summation n goes to 1 to infinity 5 upon 5n minus 1. Now, so 5 upon 5n minus 1, how you can write it? You can write n minus 1 upon 5. That is greater than 1 upon n, for all n belongs to n. So I am calling this Cn, and I'm calling it An. So this implies An is less than Cn for all n belongs to n. but this series summation n goes to 1 to infinity An, that is summation n goes to 1 to infinity An is divergent by remark. What was that remark or not? Let me check. Yeah, it was not. By not. Okay, divergent. Now, summation n goes to 1 to infinity An, that is summation n goes to 1 to infinity 1 upon n, and summation n goes to 1 to infinity Cn, that is summation n goes to 1 to infinity 5 upon 5n minus 1 are series with non-negative terms such that An is less than Cn, and the series summation n goes to 1 to infinity An is equal to summation n goes to 1 upon n diverges by comparison test. The series goes to 1 to infinity Cn is also divergent. It means summation n goes to 1 to infinity 1 upon the series uh, 5 upon 5n minus 1 is also divergent. So this is done. So today's lecture up to this. If you have any problem related to this lecture, you can comment on my YouTube channel. Like, share, comment and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you very much. We will see you for next lecture.